we would like to start talking about triple integrals. And as usual, let's start with the simplest possible domain of definition. So we're going to have a box whose faces are parallel to the planes. Such a box would look something like this. So U is equal to A1, B1 cross A2, B2 cross A3, B3. So this is the set exactly of all points whose first coordinate belongs to A1, B1, the second coordinate belongs to A2, B2, the third coordinate belongs to A3, B3. Even though it's not the simplest thing to draw such things, let's just give it a try. Computer-generated image would be so much better. But let's say that A1 and B1 are somewhere here, and then let's say that A2 and B2 are somewhere here, and let's say that A3 and B3 are somewhere here. So what would this look like? So first of all, let's understand what the projection of this box on the XY plane would look like. And then what we need to do is take this and elevate it to the height of A3 and then to the height of B3. So if I were to just mimic a segment that is almost equal to the segment from 0 to A3, then this would allow me to bring this box up to this point right here. So let's do sorry about this. I used the wrong tool. Let me see if I can erase this. It erased more than I wanted it to erase. So let's go back and complete our text. So triple integrals over general domains. And the axes were a little destroyed. So this is A3, this is B3, and I'm back where I started. So let's try to draw this box elevated at this point right here. Like so. And then let's also elevate it to height B3. So I need to go a little bit higher, like so. And then let's construct another rectangle, which is parallel to the one we just constructed. And that's our box right here. Okay, like I said, a computer-generated image should be much nicer, but this is an approximation of what this could look like, what this domain could look like. And pretty much, let's suppose that we have a continuous function on, so f of x, y, z, a continuous function on u. And we would like to give meaning to the integral over u of f of x, y, z, dv. So this is what we would call a triple integral. And now, what would a triple integral represent? Again, here, one could have Riemann sums that cannot be drawn because that would require 4 dimensions. However, we can actually think of the numerical value of this integral as a 4-dimensional volume. So if we were in 4D, we would take the domain of definition, the graph, and then the region lying between it would be would have volume, four-dimensional volume equal to the numerical value of this integral. And again, we would have the specification of the sign. If things are above the, in that case, it would have been the XYZ hyperplane, that's what we call it, then it would be positive. If it was below, it would be negative. If it had parts on both sides, then it would have a sign corresponding to the larger of the two parts. The point is that we're not going to be drawing those four-dimensional figures because we can simply not draw such dimensions. But the computation of such an integral, as we might guess, will be reduced to the computation of an iterated integral. So it turns out that f of xy z dv, and here v obviously stands for the word volume, will be a triple iterated integral. So you start from a1, b1, you integrate this function with respect to x. Once you integrate it with respect to x, then the dependence upon x disappears, and what you have really depends on y and z. So then you can integrate it from a2 to b2 with respect to y. Now the dependence upon y also goes away, so now you have a function just depending on z. And finally, you integrate that from a3 to b3 with respect to z. And please understand that here you could actually choose a different order for the variable. So for example, you could integrate first with respect to y, then with respect to z, then with respect to x. In particular, there are 6 possible ways to choose the order in which you can write this triple iterated integral. In the case of double integrals, we have just 2 ways. I mean, if our variables were x and y, we could go dx dy or dy dx. So here we have 6 ways. And let's try to do an example. Let's see how this works. So let's take, for example, the triple integral over the box that, so 0, 1 to 0, 2 to 0, 3. And I just took it this way so that the domains do not coincide and you can see where each thing goes. And let's take a very, very simple function, xy plus z, let's say, and dv. And we begin by writing this as an iterated integral. So this will give us the integral from 0 to 1 of xy plus z dx, and then 0 to dy, and then 0, 3 dz. Let's carry out the first integration. So if we take the antiderivative with respect to x, y, and z are thought of as constants, then we will have x squared over 2 times y plus xz from 0 to 1. And this would run from 0 to 2 dy, and then from 0 to 3 dz. And this would give us 1/2 y plus z from 0 to 2 dy and 0 to 3 dz. Now we need to take the antiderivative with respect to y, and we would get something like y squared over 4 plus yz, and this should run from 0. Oops, why did I write yz? I don't want to erase, you saw what happened before, and that should go from 0 to 2. And the whole thing will be from 0 to 3 dz. Now we plug in 2 for y, and that would give us 1 plus 2z, and the integral from 0 to 3 dz. Finally, you can hand this integral to any friend of yours that has taken Calc 2, and this will be z plus z squared from 0 to 3. So here you will get 3 plus 9 is 12. Okay, and that's a simple computation. However, I would strongly advise you to pause the video and try, actually rewind it, go back, try to do it yourselves a couple of times just to make sure that you get comfortable with it. And what would be really useful is to try to actually do this in a different order. So integrate first with respect to x, then y, then z, like I did it, and then try to go first with respect to z, then with respect to y, then with respect to x, or some other order. Obviously, you should find the same answer no matter what the order that you choose is. And remember that I have talked a lot about this one property where an integral can be split, and we can clearly have this property here too. So if you ever happen to have a triple integral, let's say a triple iterated integral, so all the endpoints are constant, and the function that you have inside happens to be a product of three functions, one that depends only upon x, one that depends only upon y, and one that depends only upon z. And like I said, you're not going to have this every single time. This is not going to happen every single time. In fact, it's not going to happen that often if the first integral, if the integral is given to you like this, like we saw in the previous example, we couldn't have done that because the function xy plus z, even though it was simple, it was not such a product. And we can write this as the product of three integrals in one variable, one integral in x, one integral in y, and one integral in z. And that's it. Okay, so again, maybe we all deserve an example here. So if you happen to have something as pleasant as ln of x over 1 plus y squared, what else can we put to make it interesting, times 2 to the z, and then you wanted to integrate this from 1 to e dx, and from 0 to 1 dy, and from 0 to ln of 2 dz. So let's say that this was the box that was initially given to you, then you can actually split this, and this will go as the integral from 1 to e of ln of x dx, then the integral from 0 to 1 of dy over 1 plus y squared, and finally the integral from 0 to ln of 2. Actually, I was thinking that this would give us a nice number. It won't give us a nice number, but let's see what it's going to give us. Something actually pretty weird here. But let's say that this is what we have. Let's see the computation of each of these integrals separately. They're all interesting. So the first one, remember, this is pretty much the number one example in integration by parts, right? So you have the integral of ln of x, and you think of this as the function 1 as being the derivative of x, and this is x ln x minus the integral of x times 1 over x dx, which gives you x ln x. And this is the function 1, which means that its integral is minus x plus c. So in any case, this will be x ln x minus x from 1 to e. If you plug in e, it's kind of interesting. You get 0, actually. Why? Because ln of e is 1, and you get e minus e, which is 0. So your only hope to get something non-zero is plugging in 1. If you plug in 1, again, ln of 1 is 0, but then you get minus 1. So you get minus negative 1, which is 1. How about this one? This one is kind of interesting. So the antiderivative of 1 plus y squared would be arctan of y. So you will get arctan of y from 0 to 1. And how much is this? Arctan of 1, meaning the arc whose tangent is 1, is simply pi over 2. Pi over 4, I'm sorry. And the arc whose tangent is 0 is 0. So you get pi over 4. Finally, for this one, the antiderivative of this one is 2 to the z over ln 2. And you have to go from 0 to 2. Like I told you, I thought I was doing something useful here. But with ln 2, you're going to get a pretty weird number. And we shouldn't shy away from this weird number, 2 to the ln 2 minus 2 to the 0, which is 1, divided by ln 2. And the final answer will be pi times 2 to the ln 2 minus 1 over 4 ln 2. Okay, that's what you get if you multiply the three numbers together. And this is an example of an integral that splits. We saw an example of an integral that doesn't split. But now we need to go to the more interesting cases. So again, the idea is what happens when you're integrating over a set which is not a box. And here's where, again, we mimic what happened in two dimensions. So basically, the situation that we will be able to handle is the following. When the domain U is like this, so you have a two-dimensional domain, first of all, on the xy plane. And then you have two functions. One that has this graph up here. So let's say that this is z is equal to g2 xy. And then you have another graph down here, right? Both of these are graphs of functions that are defined on the set D. And your domain is simply the region between them. So this is the domain U. And we can describe U as all the xyz's such that z lies between g1 of xy and g2 of xy, and xy is in D. So this is what U is. So then if somebody asks us, what is the triple integral over U of f of x, y, z dv? Again, our goal here is to be able to process this domain and write the integral as a triple iterated integral, right? So here's what is going on. What we do is perform first vertical integration. When I say vertical integration, I mean in the z direction. So you start by integrating this in the z direction. And of course, if you choose a point xy, if you fix a point xy, then the limits that you're going to find here, let me actually change color and show this a little more clearly. So you have the point on the graph corresponding to xy here. And if you ask what numbers these are, this will be exactly g1 of xy. That's how a graph works. And this would be g2 of xy. So what you're going to have here is the integral from g1 of xy, g2 of xy. And now once you compute this one integral, then what you get here depends only on xy. And this is the beauty of it, that I'm not going to try to represent it as a triple iterated integral, even though this is what is going to happen in the very end. Instead, what I'm going to tell you is, since now you are reduced to a double integral, just take this double integral and compute it any way you like over D. Okay, so basically what I'm saying is that if you have a triple integral, and you integrate in one direction, then you can reduce it to a double integral. Presumably, the double integral that you obtained now needs to be processed again so that you get a triple iterated integral. And this is what will happen in all possible cases that we will encounter. But regardless, what I want you to understand is that conceptually, we just need to take one step and say that now we're reduced to a double integral, and double integrals are something that we have already covered. So it's up to us to compute that double integral using one of the methods. I mean, you could use polar coordinates, you could use anything else that you like for that double integral. And please understand that this was done by, in the case that the domain looks convenient like this in the z direction, but you could have had a domain that actually does this in the x direction or the y direction. And you could have integrated first in the x direction and obtain an integral in y and z, or integrate in the y direction and then obtain an integral in x and z. So again, it would be interesting here to do an example where we don't focus on the integration itself, but rather on the iterated integral. So we don't reveal what the function f of x, y, z is. And here's what I'm suggesting. Let's go to the unit ball. So the unit ball is the domain which is bounded by the unit sphere. So the unit sphere has equation x squared plus y squared plus z squared is equal to 1. So let's say that we want to go in the, so let's say that this is u. So u is the interior, along with the boundary, of course. You can also take the boundary, and it doesn't really matter whether you take it or not. But so you have the triple integral over u of a function f of x, y, z that I couldn't care less what it is at this point. And what is important is to try to express u as a domain in the way that we showed before. So this is actually quite agreeable in the z direction. And in the z direction, now remember how in the case of double integrals, we were saying upper boundary and lower boundary, where here again, we will have exactly this. So we will be talking about upper boundary and lower boundary. But we will actually have a our upper boundary will be a surface, and the lower boundary would also be a surface. So what we will have then is we will need to use the equation of the sphere and find what the surfaces are. So the upper surface would be z is equal to square root of 1 minus x squared minus y squared. So we solve for z, and the lower surface would be z is equal to square root of actually negative square root, negative same square root, 1 minus x squared minus y squared. So now we're ready to do our integral. And let's give ourselves a little bit of space here. You can see why. So we will have minus 1 minus x squared minus y squared and square root of 1 minus x squared minus y squared. Then you have the function f of x, y, z, and you're integrating with respect to z. Let me actually complete the description that I start here and never completed. So this is the set where z is between negative square root of 1 minus x squared minus y squared and less than or equal to square root of 1 minus x squared minus y squared. And then we would like to see what happens with the domain of these two surfaces that can be considered as graphs, of course. So the domain is right here. And sometimes it's useful to draw the domain as a two-dimensional, and we process the domain before, and the domain happens to be just x squared plus y squared is equal to 1. So guess what? How we're going to continue here. We're going to say that y is between negative square root of 1 minus x squared and square root of 1 minus x squared, and eventually that x is between negative 1 and 1. So in other words, here I'm just looking at the lower boundary, which is y is equal to minus 1 minus x squared, the upper boundary, where y is equal to square root of 1 minus x squared, and I'm going to perform vertical integrations, and these integrations go from negative 1 to 1. So now we can finish writing the integral. So we're going to have dy, where we have minus square root of 1 minus x squared to square root of 1 minus x squared, and dz that eventually, I'm sorry, dx that eventually will take us from negative 1 to 1. And that's our triple iterated integral. Let me make the remark that I use this domain, I use this particular domain in order to show how things can be processed in a situation like the one that we mentioned before. As we're going to see later, it's not a good idea to actually, if you have the ball, it's not a good idea to try to compute an integral over the ball by using this method. However, if we want to use this method, it renders the first part of the process into a very nice example of how to express our domain the way that is needed to be expressed. So that's a good example to see how we deal with the domain. It's not a really good example to see how we compute an integral over the unit pole. We're going to come back to this question later. And for the moment being, it might be a good idea to try to do a nice example. And let's actually compute the volume of the tetrahedron. And this is where I should mention this, that as I said in the beginning, the integral itself has not such a great, the triple integral has not such a visible interpretation. No, it's as good as any other interpretation of double or single integrals, but you cannot visualize it. However, there's one type of triple integrals that have a very nice interpretation, and that's the triple integral of the function 1 over any domain. And please understand that such an integral sometimes can be written by completely skipping the function 1. So if you integrate the function 1 over a three-dimensional domain, what you find is the volume of that domain. And I would like to do an example like this. So the example that I would like to discuss is the volume of the tetrahedron. So compute the volume of the tetrahedron with vertices A00, 0B0, 00C, and 000, where A, B, C are greater than 0. So let's draw it first. Okay, so let's draw this tetrahedron. Note that what I'm doing here can be done with methods from JustCalc 2, but This should be kind of interesting. So this says 0, 0. And let's say that this is 0, B0. Excuse me. And that this is 0, 0, C. And of course, the origin doesn't need an introduction, right? So this is your tetrahedron. And the one thing that you will need to eventually know here is how to find the equation of this plane. And this plane is a plane that goes through these 3 points. And there is an analog of the equation of the intercepts that we saw in the case of 2 variables. So this is x over a plus y over b plus z over c is equal to 1. Okay, this has this equation, and obviously we will need this equation in order to express our domain in the way that we saw before, so that we can write our triple integral. So this is all the x, y, z's, and now you have an upper boundary that you can find by solving this equation for z. So this will be c times 1 minus x over a minus y over b. And so z will be between 0 and c times 1 minus x over a minus y over b. And then here we said at this point it might be useful to draw the 2-dimensional projection of this, which is this thing right here. And so here you go from A0 to 0B, right? And you're looking pretty much at this domain. This line now is x over a, again, the interception in the equation of intercepts is equal to 1, which will give you that y is between 0 and b times 1 minus x over a, and eventually x is simply between 0 and a. So we have our domain. We just need to integrate the function 1. So let's take a deep breath and do it. And allow me to change page here in order to give myself enough real estate. So I want to compute the volume of the tetrahedron. And now let me write it as an iterated integral. Again, give myself enough space. I have the function 1 is my integral, and I start with z. And I know that z will go from 0 to c times 1 minus x over a minus y over b. And then I'm going to proceed with respect to y, and I know that y is going to go from 0 to b times 1 minus x over a, and dx is going to go from 0 to a. So what do we have here? Let's do this iterated integration. It's actually very useful. This is exactly the point where you have to just leave behind any hope that this integral is going to split. I've seen people try to split this. It can split. Why? Because the endpoints are not constant. So you will have to do iterated integration for sure. So what do we have? We have the integral from 0 to b times 1 minus x over a. I'm taking the antiderivative of 1 with respect to z. That gives me z from 0 to c times 1 minus x over a minus y over b. And this will be done with respect to y. And finally, from 0 to a dx. So what we need to integrate is the following function. And here, it's a polynomial. How hard can it be to integrate a polynomial? You just have to be careful what is constant and what is non-constant. But I think this is a very fun integration. I'm going to show you a little trick here, or a little perspective for that matter. So here's what I want to look at. So I'm integrating with respect to y, right? So this whole thing here then I see it as a constant. All of this thing here, I see it as a constant. I think of it as the number 7, right? So then the one integral that I want to have in mind, that I remember how it's done, is this integral right here. So, and let me give it to you in one variable. So if I have the integral of a plus bx, then dx, then, and this can be done by using a substitution, but this is a plus bx squared over 2, and then you simply need to divide by the coefficient of x, 1 over b. Like I said, you can easily find this by substituting, by using the substitution u is equal to a plus bx equals u. So that's what I would like to do right away here. So if you allow me, I will write this. Actually, I will write it as the integral. So I have the c, I have this c in front, and then I need to divide by the coefficient of y. But the coefficient of y is negative 1 over b. So when I divide by it, I will get simply minus b. And then don't forget that there's this 2. So I'll put this 2 here. And then I will have simply 1 minus x over a minus y over b squared. And this should go from 0 to b times 1 minus x over a. And the whole thing needs to be integrated from 0 to a with respect to x. And here's the magic. Try to see what will happen if you plug in b times 1 minus x over a for y, right? If you do that, the b and the b are going to cancel, and you will get 1 minus x over a. Yes, but that's exactly what you have here, 1 minus x over a minus 1 of minus x over a. Believe it or not, you get 0 if you plug in b times 1 minus x over a. So the only interesting thing that you get is when you plug in 0, where you get simply 1 minus x over a. And that sign that you have in front is going to also disappear. So you're going to have the integral from 0 to a. And let me take those two things out. bc over 2 times 1 minus x over a squared. That's what we get, dx. And then finally, I can play the same thing here, which is, again, just a way to avoid the substitution. So I will get minus abc over 2. And what is the antiderivative now of u squared? It's u cubed over 3, right? So I would get the integral from 0 to a of 1/3 1 minus, oops, I shouldn't have done integral here because I found the antiderivative. So this will be minus abc over 2, and it will be 1/3 1 minus x over a to the 3rd power from 0 to a. If you plug in a, guess what you get? 0, right? Because it's 1 minus a over a. If you plug in 0, this number becomes 1, and you just get an extra negative sign because it's the part that is being subtracted, and that gives you abc over 6, which is the final answer. That's the volume of the tetrahedron. It's a really lovely computation. You can try to do it without the tricks that I showed you, just by trying to integrate in a more traditional way. But I think these tricks are worth noting, and I hope that you enjoyed this example. Thanks for watching.